Welcome everyone. This is Detecting Exploits with Novel Hardware Performance Counters and ML Magic. Before we begin, a brief introduction to who we are. So I'm Gregory. I'm a research scientist at Capsule 8. Have a background in low-level systems and binary exploitation. I'm a recent graduate of NYU Tandon and the Osiris Lab, shout out, where I'm actually also now a hacker in residence. My contact info is on screen if you wanted to email with questions, ideas, anything like that after the talk. Happy to talk.
Hello everyone. My name is Harini Kannan. I am a data scientist at Capsule 8. My background is in business statistics. I'm currently working on system user behavior profiling, text analytics, interpretable MLOps. You can hit me up at Twitter, at Jarvision, or through my website. So without much ado, let's get started. Over to Ghost.
So introduction to the talk. What are we going to be covering? So first we're going to be covering what hardware performance counters are and why they exist. Then we'll be going into some prior work that Harini and I have done, specifically on detecting Spectre and Meltdown, but with documented counters. Then we'll be going into this work, particularly what these undocumented hardware counters are, and kind of exploring them a little bit. We'll be then training models on undocumented counters, seeing what we can detect with these trained models, and doing a little bit of interpretation on the results. Again, given that these are undocumented, we can't know for sure exactly what they're measuring, but we have some ideas. And lastly, we'll go over some future work ideas, of which there are plenty. So the main question that we're out to answer is, can we detect exploits using undocumented hardware performance counters on Intel CPUs? It's a mouthful. So first, what are these hardware performance counters that we've been talking about? So they're also known as performance monitoring counters. Basically, they're hardware devices that count events as they happen in a couple of different performance monitoring units, or PMUs, inside of the processor. They're usually used to debug things like system slowness or program slowness, measuring things like cache misses, total number of instructions run, things like that. But as we'll see, they have a lot more uses as well. Specifically, we'll be focusing on the CPU PMU today. That is the performance monitoring unit that lives on each core or on each hyperthread in a modern CPU. Most modern Intel CPUs let you pick 4 or 5, depending on the exact generation, counters to monitor at once if you're on a hyperthread, or 8 or 10 if you're on a non-hyperthreaded core. And you specify what you actually want to measure to the processor as 2 8-bit integers, an event ID, and a UMask. Broadly speaking, the event ID is the category or kind of the subsystem that you're wanting to measure. So the branch predictor or the caches, something else like that. And then the UMask specifies exactly what counter you're interested in within that. So L1 cache misses or conditional branch mispredicts. On Linux, you interact with these through the perf subsystem and usually through the perf CLI. There are some examples up there if you wanted to mess around. The first one, as you may guess, measures the number of cache misses that the processor has while running binls. And then the second one is specifying a specific event ID and UMask, and that one in particular you'll actually see show up in our models later. It's also worth noting that there's a couple different ways to actually sample these counters from the CPU. You can get them on a timer basis, so every n milliseconds. You can get them when the counter overflows a certain value, so when it reaches a threshold. Or you can just let them build up the entire duration of the program run, which will be what we'll be exploring to start with. So a couple of years ago, Spectre Meltdown happened. For those who didn't hear at the time or haven't heard since, they're CPU level vulnerabilities that abuse processor speculation. Basically, modern processors speculate what code should be run before they know for sure to make your code faster. This introduces a lot of ways to do bad things, though. So Spectre v1 was speculating through a bounds check. So in your speculated code, you could read, or past the end of an array, for example. Spectre RSB let you speculate through a bad return address, the Spectre return stack buffer. You could speculate reading a disabled FPU, which was lazy FP, so potentially leaking secrets from other processes on the system entirely. And there's a bunch more. So a bit of background here. These speculative execution attacks by themselves don't do a whole lot, right? You can speculatively execute code, but can't do anything with that because all of the actual artifacts they don't get committed to the system state. So what you can do is use a separate exfiltration technique like Flush+Reload to actually exfiltrate data out of the speculative execution. So the one we'll be talking about today is Flush+Reload, which is pretty consistent and easy enough to do with assembly level access. This can be done through like a JavaScript interpreter, for instance. The basic idea is that you have a timing array, and before you run whatever part of code you want to get data out of, you CLFlush that entire array out of memory, or out of cache, so that any accesses to it will force a memory read. You then go through with your speculative execution and have the speculation load a cache line. And what that'll do is mark a cache line active, and then when you come along later, read through all the cache lines in the array, and one of them will read faster than the others, because the other ones are still reading from main memory because you CLFlushed it earlier, but one of them will be fast because you loaded it during speculative execution. And that side effect on the CPU doesn't get thrown away when the processor realizes it's misspeculated. So a hypothetical example here, this is super oversimplified. Cache lines are like 1 byte in this example, so it's obviously not real, but just to get the point across, let's say you have a conditional branch that is slow to load and usually true. So the branch predictor encounters this and says, okay, let me go dispatch the actual read, but let me try and continue into this next instruction, speculating that the conditional will come back true. So in the speculation, we now load from secret number and load a cache line in our out array, which is our timing array, based on the secret. So in this case, we're masking off the low 2 bits, and we're saying, let's load from that. So that'll make, in this case, the third cache line active. Now, eventually, the load will originally come through, and the processor will realize it misspeculated, and will throw away all the architectural state, but leave the cache line active. So we can come along later and measure how long it takes to actually access all of these, and we'll find that the first 2 are slow, but the third one's really fast because it's already in cache. And so with this, we can leak that at least the low 2 bits of our secret number are 2. So we developed detections for Spectre and Meltdown using 3 counters early in 2018. We used the total number of cache misses, the number of cache references, and the number of branch misses. The first 2 form effectively the cache miss ratio, and then the third was actually chosen just by experimentation, but makes sense kind of looking back after the fact. Basically, it normalizes to the complexity of the program. So the idea is if a program is branch mispredicting a lot, it's also likely to cache miss a lot. Just it's not well optimized or it's doing something really weird. So we sample all of these counters on 100 millihertz, did it again, on 100 millisecond ticker. And this technique detects all of the public proof of concepts that we've tried. So this is a visualization of the SVM model that we built around this. Harini will go into details about what this actually means later and what SVM is. But roughly speaking, you can see the green dots are non-attacks. They're benign programs running. The red dots are attacks. They're instances of the Spectre proof of concept running. And you can see basically we've successfully drawn circles around all the red dots, which means we've caught the attacks. Specifically, if we actually look at the accuracy, if we combine the SVM model and a deterministic model, which is just cache miss ratio and branch miss ratio below a certain threshold, we can see that we get 100% accuracy and a 0 false negative rate. So we have effectively a perfect detector here for all the proof of concepts that we've tried. However, this detection can actually be really easily defeated if you know what it's looking for. So all you have to do is mix in some cache-friendly code into the proof of concept. an example like this, you have this stuff array, which we effectively always keep in cache, and excuse all the register old C style nonsense. I just wanted to make sure that this doesn't end up writing something into the stack, which modifies the cache in another way. This just does what I think it does, and sure enough, this will bypass our detection. We can even tune using the high bound of the round parameter what our cache miss ratio, what we want it to be, so we can mimic anything. So with that done, let's dive into our current research. So as I mentioned earlier, hardware performance counters are specified with two 8-bit integers. So we actually have room for 65,536 counters, potentially. But only a subset of those are actually documented by Intel. Somewhere in the low hundreds to 1,000-ish, I think 1,500-ish was the most they've ever documented. But that's not to say that the ones that aren't documented don't have any data behind them, that they're not counting anything. So the idea basically came about, what if we read all of the counters, even the undocumented ones? By doing this, we're basically turning this exploit detection problem into a black box ML problem, so just completely changing frame. So what are we going to run these counters on, though, I guess is the question that arises. So we have 4 sample programs that we were running on. We have a minified exit 0, which is basically there just to detect any overhead of the kernel actually starting the process. We have a scikit benchmark, which was known from prior research just to be something that had a very high cache miss ratio. So it sort of looks like Spectre. We had the Spectre proof of concept itself, and then we had our modified Spectre proof of concept with our cache-friendly code mixed in. So once we gathered all that data, we did a few filtering steps. We removed all the counters that were always 0, just because they weren't doing anything. We removed counters that had a difference between scikit and Spectre less than 95%. So the idea is basically we want things that are very different between scikit and Spectre. Then we removed counters that differed more than 5% between our modified Spectre v4 and the original proof of concept. Again, the idea being those two should give a similar signature, because we want to actually detect the exploit running, not like a side effect of it. So since those are at their core doing the same exploit, they should be relatively similar in their counts. At the end of that, we were left with 81 counters, and interestingly enough, none of them were documented. So we thought, okay, maybe we're actually on something here. It's worth noting at this point that all of our tests were run on a Haswell machine and an Ivy Bridge machine, so a bit older microarchitectures, but what we found should still be valid with adaptation on newer microarchitectures, but the results will differ, because again, these counters change from generation to generation. So we came up with 2 data sets of counters that looked interesting. The first one is one that we'll be covering from here on out. The second performed almost identically, but we just don't have time to cover both of them. And interestingly enough, you'll actually see one of the counters appears in both, which turns out to be a very significant counter.
All right. Now that we have zeroed in on which undocumented counters we want to use as features for our models, let's see how the experiments went. So the exploits of interest for us were Meltdown, aka Spectre v3, which is the rogue data cache load, Spectre v1, which is the bounce check bypass, Spectre v2, which is the branch target injection, Spectre v4, which is the speculative store bypass, ghosting Spectre v4, which is the same as Spectre v4 but with invasive changes that Ghost made to make sure we bypass the existing detections using known performance counters, right? We were also curious to see if we can detect ROP and stack pivot attacks using these same undocumented per features, and surprisingly we could. Let's see how. So for the data collection, we are using Linux perf counters, of course. And along with the exploits mentioned before, we also collected data for the following baseline programs. They were libgid unit tests, scikit-learn benchmark tests, Phoronix nginx test suite, and Linux defconfig compiler. And we selected, these selected counters were measured for every 100 milliseconds, and each of the test script was run 5 times for statistical significance, right? And these were the model metrics that we calculated: precision, recall, F1 score, false positive rate, false negative rate, area under the curve, test accuracy, and confusion matrix. Now, before going to the numbers, let's quickly see what each of the metrics mean as a quick summary. So precision is the ability of a classifier to not label a true negative observation as positive. It's the proportion of positive identifications made by the classifier that are actually correct. So it's basically the percentage of your results which are relevant, right? Next is recall. Recall is the ability of the classifier to find positive examples. Basically, what proportion of actual positives were identified correctly. So if we want to be certain to find all the positive examples, we could maximize recall, right? The next one is F1 score. F1 score is basically the harmonic mean of precision and recall, and it ranges from 0 to 1, so you want it to be as high as possible, as close to 1. So instead of seeing precision and recall separately, you can just look at the F1 score and look at the goodness of the model, how good it is. The next one is area under the curve. This is an important metric for any classification problem. The RC curve represents the true positive rate and false positive rate for all probability thresholds of a binary classifier, right? The AUC evaluates the overall quality of the model. So more the area under the curve, the better, right? So in the plot, you can see in the left, in the x-axis, you can see the false positive rate. In the y-axis, you can see the true positive rate. So you want the plot, the graph, to be pulled as close to the left top quadrant as possible, right? You want the lowest false positive rate and the highest true positive rate, right? So this is a good metric to measure classification model. The next one is confusion matrix, another important one. This is also known as error matrix and is a specific table layout that allows visualization of the performance of an algorithm, right? Confusion matrix visualizes the accuracy of a classifier by comparing the true and the predicted classes. As you can see, the diagonal squares are the correct predictions, and the off-diagonal squares are the incorrect predictions. In the plot, you can see the y-axis is the true class, and the x-axis is the predicted class. So that makes all the diagonals as the true positives and the true negatives, right? So you want them to be as high as possible, and you want the off-diagonal squares, which are the wrong predictions, to be as low as possible. So next we'll see the algorithms that we have used. These are the algorithms that have performed the best for us. The idea was to start from the simplest, most interpretable model and go up from there till we get good results. And these are the 4 models that have worked really well for us so far. The first one is support vector machine, random forest, extreme gradient boosting, which is the XGBoost, and histogram based gradient boosting. Now we'll quickly see what each model does, like a quick summary. SVM is a supervised ML algorithm which can be used for classification as well as regression. Obviously we are using here for binary classification. In SVM, we plot each data item as a point in n-dimensional space, where n is the number of features you have and the value of the feature being its coordinate. Then we perform classification by finding the hyperplane that differentiates the 2 classes. As you can see in the plot on the left, The objective is to maximize the distance between the nearest data point of either class and the hyperplane that separates it. Right? For us, the hyperplane is not linear, but it was RBF kernel, radial basis function. You can see the decision boundaries of different kernels in the second plot on the right. All right, the next one is random forest. It's an ensemble method where multiple decision trees are created using random subsets of features and bootstrap data. Each decision tree then votes by predicting the class. The votes are then tallied to reach the final prediction before seeing the next model, which is the XGBoost, and which also performed the best for us. Let's see the basic behind the scenes difference in concept for both these models. Random forest uses decision trees which are very prone to overfitting. In order to achieve higher accuracy, random forest decides to create a large number of them based on bagging. Now, bagging, the basic idea is to resample the data over and over again for each sample, and it trains a new classifier. Right? So different classifiers overfit the data in different ways, and through voting, those differences are averaged out. Now, GBM, gradient boosting method, is a boosting method which builds on weak classifiers. The idea is to add a classifier at a time so that the next classifier is trained to improve the already trained ensemble. Notice that for random forest, each iteration, the classifier is trained independently from the rest, whereas it's the opposite for XGBoost. Right? Now, XGBoost, which is extreme gradient boosting, this was the best model we had. It builds on weak classifiers, as we saw before. It adds one classifier, decision tree, at a time, so that the next classifier is trained to improve the already trained ensemble, right? The next model is histogram-based gradient boosting. It's a very similar model to XGBoost. It's a faster implementation of gradient boosting classifier when the number of samples is high. It bins the input samples into integer valued bins, which reduces the number of splitting points to consider. This allows the algorithm to leverage integer-based data structures instead of relying on sorted continuous values when building the trees, right? Now, let's detect Spectre again, but this time even the ghosting Spectre, which evaded us before. Here you can see the summary of all the models that we have tested so far. The first three columns shows the features themselves, 3698, 40E3, and EFF4. The next column shows the Intel architecture. It's either Ivy Bridge or Haswell, and the four models that we have tested that worked really well, which are SVM, XGBoost, Random Forest, and HGBoost. And then you can see all the metrics that we talked about before: precision, recall, false positive rate, false negative rate, area under the curve, and accuracy. And then you can see whether these models detected the attacks that we fed. The green colored rows, as you can see, have the models that are doing really well, and they are detecting all the attack variants, all the Spectre and Meltdown variants, right? Let's see the best model that we had so far, which is the XGBoost, using the three features that we saw. And the metrics here, you can see it has 99% precision, 98% recall, 0.04% false positive rate, 4% false negative rate, and 98% area under the curve. Now, false negative rate here doesn't imply that the attack itself was being missed. It just shows the part of the exploit that was being missed. So all the, as you can see in the table before, all the attacks were caught by this model. So the false negative rate just shows the part of the exploit that was missed. So the next, you can see the area under the curve for the best model, which was XGBoost. Here you can see two plots. The left one is for the test data set, and the right plot is for the holdout dataset. So the Spectre v4, the edited one, the ghosting Spectre v4, was part of the holdout dataset. We wanted to make sure the model has never seen that variant before, and we wanted to test whether it can still detect the newer variant when trained on other existing variants, right? And it did. So that's why it's super interesting. So you can see in the left plot, the test accuracy was 99.8%, area under the curve was 98%, false positive rate was 0.04%, and false negative rate was 4%. And the F1 score was 98%, which is good. Now let's see how it fares in the holdout dataset. It fares better than what we saw in the test dataset. You can see the test accuracy was 99.9%, area under the curve 99.6%, 0 false positive rate, and 0.68% false negative rate. So it caught almost all parts of the attack, and 100% F1 score, which is great. Now let's see the confusion matrix for the same model, right? Again, the left shows the normalized confusion matrix for the test dataset, and the right plot is for the holdout dataset, which had the edited ghosting Spectre v4, right? So again, as we saw before, we need the diagonal to be as high as possible and the off-diagonal squares to be as low as possible. So the left top quadrant, which is the true negatives, 100% of the non-malicious baseline data points have been classified correctly, and 96% of malicious attack data points have been classified correctly, which is great. Now let's see in the right plot for the holdout dataset, 100% of baseline non-malicious data points have been classified correctly, and 99% of malicious attack data points have been classified correctly. So it definitely fares better than any other models that we have seen so far. So next, let's look at some model interpretation. This is a topic that I'm very fond of. So here we will see the model interpretation using the SHAP library. It's a Shapely additive explanation. It's based on Shapely values technique used in game theory to determine how much each player in a collaborative game has contributed to its success. So here, each SHAP value measures how much each feature in our model contributes to the prediction, either positively or negatively, right? So here we'll see the feature importance for the XGBoost model. EFF4 seems to be the most important feature, followed by 40E3, followed by 3698. Now, how each feature impacts the target variable, let's see. So the next one, the plot that we're going to see is partial dependence plot. So this shows the marginal effect that one or two variables have on the predicted outcome. Whether the relationship between the target and the feature variable is linear, monotonic, or more complex. So let's see the partial dependence plots for each of the three features separately. So the first one we'll see for the most important feature, which is EFF4. You can see it clearly influences the outcome variable negatively, helping the model classify the baseline data correctly. So if you see, there is a big cluster of blue data points. So the blue data points here denote the non-malicious baseline data points, and the red ones denote the attack data points, right? So there is a huge cluster of blue on the top left corner, and clearly, higher the SHAP value for EFF4, there's a clear delineation where it classifies the baseline data correctly. And in the right y-axis, you can see another feature, 3698. This shows that EFF4 interacts slightly with 3698, which is the other feature, where the value of the 3698 feature are between 10K and 30K, right? So there is definitely a small interaction going on there, but EFF4 clearly, with its huge negative influence on the model, helps it to classify the baseline data points correctly. The next one is for the second feature, which is 4DE3, the same partial dependence plot. It clearly shows there is approximately a linear positive trend between 4DE3 and the target variable, right? Higher the SHAP values for 4DE3, the classification becomes 1, which is malicious, right? So there is an approximate linear relationship there, and it clearly doesn't react with any other feature. As you notice, there is no y-axis on the right side, meaning there is no other feature that's interacting with this feature, which is 4DE3, which is great. The next one is the last feature, which is 3698. This has a significant impact that can be seen for the highest and the lowest values of the feature, right? If you see in the rightmost corner, right top corner, there's a cluster of red data points, and in the left bottom corner, you can see there's a cluster of blue data points. So there is a clear impact for the highest and the lowest features classified as malicious and non-malicious respectively. And there's also some interaction going on with the feature 40E3, as you can see in the right y-axis. There's interaction for the values of 40E3 lying in between 75,000 and 300,000. If you see the parallel red and blue dots, right? So definitely some interaction going on. The next plot is called force plot. The first plot shows the interpretation of the prediction using logistic regression, right? The red color denotes features that push the prediction higher to the right, and those pushing the prediction lower are shown in the blue color, right? In the first plot, it shows for one data point amongst the whole test data set. So this is just for one data point. And in this case, it was a positive one. It was a malicious one, right? The features 40E3 and 3698 have the most positive impact on the prediction being malicious. That's one. And the feature EFF4 has the most negative impact, right? It's bringing it down. So you rotate this plot 90 degrees and plot the same for all the data points in the test data set together, and you get the second plot, right? Each data point here is a vertical line. It clearly shows feature EFF4 has a negative effect on the outcome variable, and the other two features push for the outcome to be 1. That is malicious. This intuitively retraced the feature importance graph, where EFF4 is the most important feature, responsible for making sure the baseline non-malicious programs are classified correctly. And the other two features play their secondary roles to push the classification towards 1, for the malicious data points. Here, you can see the same force plot for each feature being filtered out, right? Here's the force plot filtered just showing EFF4. Clearly, the blue dominates, right? Showing its negative impact, negative effect on the outcome variable. The next one is the force plot for 40E3 filtered, right? Clearly, it has a positive impact and helps the model push across the line to classify the malicious data points correctly. Now let's see the force plot filtered just for feature 3698. This again has a positive impact on the target variable, though not as strong as 40E3, but helps the model push across the line to classify the malicious data points correctly.
Thanks, Harini. So at this point, we've seen that we can detect Spectre and variance really well using undocumented counters. works, but we wanted to see if we could detect other exploits, specifically ROP. There's been prior work done on detecting ROP with hardware performance counters or other hardware performance monitoring things like the last branch record and Intel processor trace. The main thing with LBR and PT is that there's a lot of data, right? It's measuring everywhere that the program is running, and so you just end up with a lot of overhead in actually trying to run these detections. In theory, ROP should also have a signal in branch mispredicts, right? ROP chains make the return stack buffer and the processor basically useless because you're returning all over the place to places where you're not coming from. Problem here, though, is that ROP chains are really short, right? You're looking at kind of 50 to 100 instructions at most. You definitely could have longer ones, but there's often not a need for it. And so you're dealing with 50 to 100 branch mispredicts, which in the grand scheme of things just really isn't that much. So we wanted to take a crack at it, though. So we ran a ROP exploit that I developed about 100, or so we ran a ROP exploit that I developed 100 times per cycle to maximize whatever signal we could find, which obviously means that the data from this is not really productionizable. It just means we're just looking to see if there is anything to be there or to be seen there in the first place. We also added a new baseline program, which did exactly what the ROP chain did, but without ROPing. So same syscalls, same memory creation, same stack pivoting, all that. And this is just to make sure that we're actually picking up the ROP chain itself and not side effects of whatever the ROP chain is doing. And crazy enough, after running all of this and crunching the numbers, the exact same counters work for ROP as did for Spectre and Spectre variants. And this absolutely blew my mind the first time that we got the data back for this, because this just doesn't make any sense. And so I spent at least a good few hours trying to figure out, like, how did we mess up? There must be something wrong here. What did we do? But no, it turns out, as you can see, we're doing pretty well. It's definitely not as good as our Spectre detections were, but it's better than the coin toss, much better than the coin toss. As you can see from the confusion matrix, the main problem that we have isn't in false positiving on normal programs, it's that we don't always pick up the ROP chain, which again leads back to what we've seen before with using the branch predictor and branch misses. But using these undocumented counters, which again seem to not have anything to do with the branch predictor because they also picked up Spectre, we're still getting 77% malicious classifications correct. So there's a lot more research to be done in this bit because, again, this just does not make much sense, but nonetheless, it's how it is. So now that we know all this, now that we've covered basically everything else, I want to spend a little bit of time talking about interpreting these results, the little that we know about it. So for Spectre, there's a single support file inside of Intel vTune, which names the EF event ID as core snoop response with the helpful description of TBD. Thanks, Intel. Supposedly, though, this is only for Skylake X and Cascade Lake, so much newer microarchitectures than what we're testing on. However, it does make a little bit of sense. The hypothesis currently is that this EF counter is detecting the CL flush somehow. If this is actually core snoop response, it could be from other cores basically acknowledging the CL flush and responding to the core where the CL flush originated. Or it could be something else entirely that's actually just completely undocumented, but it does seem to have some correlation with CL flush. The main reason we think this is that the counters actually showed that the sample program was malicious, that a Spectre proof of concept was malicious, even when the actual flush and reload exfiltration bit was broken. So we are correctly CL flushing things, we just weren't retrieving data, and this was still classified as malicious. So that's definitely an encouraging sign that we're not just picking up on some other counter that's measuring cache misses. This definitely seems to be something new and better. For ROP, very unsure. As we saw before, it's the same counter, so we know that there can't be too many other options for what the EF counter does, at least. It definitely seems to be related to CL flushing. So continuing on the idea that it has to do with cache flushing and last level cache management stuff. A couple theories. This could be detecting the embedded stack pivot in the ROP sample. Specifically, I don't know this for a fact, but if the processor keeps special store buffers around for the stack, since it's used so commonly, if RSP changes, perhaps it has to invalidate and flush all of those, which could cause a flood of effectively CL flushes. It could also be detecting the return stack buffer mispredicts in kind of an odd way. The theory is if the caches are preemptively loading based on what's in the return stack buffer, then you'll cache miss every time, right? Because your return stack buffer is saying, all right, load this, cache loads that, and then suddenly you're not returning there. You're returning wherever else the ROP chain is going. Very unsure about these, but some initial ideas. We're very unsure. So future work. The biggest thing here is, in my mind, generalizing and automating data collection. We have scripts that will run through all the perf counters for whatever program you want, but we've only done it, again, on 2 microarchitectures. So extending all of that to be done on all the microarchitectures that you could reasonably care about nowadays. And this is actually made somewhat easier by the fact that the cloud is so prevalent now. In theory, you could just buy a instance out for each microarchitecture for a couple hours, run the script, get your data, and you're done. We just haven't done it yet. There's other also PMUs to explore, specifically the uncore counters on Intel chips. Could be very promising because they also deal with cache coherency stuff, last level cache stuff. There's also AMD. AMD is a player, again, in the x86 space, and presumably has a similar pipeline architecture to Intel. I don't know for sure, but I would assume so. And so they'll also have probably similar counters, whether they actually expose ones that aren't documented, I'm not sure of, but there's research to be done there. And then, of course, there's also ARM, yet another kind of player that's up and coming on the field. With ARM in particular, there's potentially some vendor-specific internals, which could be interesting to poke at. Again, haven't done any of this yet, so they could be very boring, but there's potential there. So a couple closing remarks just to finish everything out. As I've said a couple times now, due to the nature of all this being undocumented, we really can't know for sure what's going on here. Unless Intel releases more documentation. If you're listening, it'd be great. That said, there are definitely other experiments that we could do to try and determine what these counters are counting. And so if you have any ideas for these, let us know, run them yourself and tag us in a post or something. We're all very curious now what's going on with this. So our contact info is on the first few slides again, if you want to get in touch. Otherwise, I think we're going to transition into a Q&A now. So thanks, everyone. All right, hey everyone, thanks for watching and thanks for the questions in chat. We basically don't have any time to actually respond to stuff on camera, unfortunately. So feel free to, again, contact us. I'm ghost@capsulate.com or at KLSims on Twitter.
I'm Harini at capsulate.com or Jarvishan at Twitter.
And we're happy to take your questions, talk about future research, any of that kind of stuff. And I think with that, I think we're done.
Yeah, thank you all.
Thank you.